Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about colligative properties and non-colligative properties. What is the difference between colligative and non-colligative properties? So I hope this video will be helpful to you. If you like this video, then subscribe my channel. You know friends, solutions have different properties than either the solute or solvent used to make the solution. Those properties can be divided into two, colligative and non-colligative. Non-colligative properties depends on the identity of the dissolved species and the solvent. So first I will talk about the colligative properties. You know, colligative properties depends only on the number of dissolved particles, molecule or ions, small or large, in solutions and not on their identity. Osmotic pressure, vapor pressure lowering, boiling point elevation, freezing point equations. Now compare to the properties of 1.0 m equals sugar solution to a 0.5 m equals solution of sodium chloride. Despite the concentration of sodium chloride half the concentration of sucrose, both solutions have precisely the same number of dissolved particles. Why? Because each sodium chloride unit creates two particles upon dissolutions, and sodium plus and Cl minus. Both solutions have the same freezing point, boiling point, vapor pressure, osmotic pressure, because those colligative properties of solution only depends on the number of dissolved particles. Other non-colligative properties including viscosity, surface tension and solubility are different. So osmotic pressure, diffusion in liquid. You know friends, substance tend to move or diffuse from the region of higher concentration to region of lower concentrations. So the differences in concentration disappear. Friends, by placing water solvent on concentration equals salt solutions, salt moves into water layer and water moves to salt solutions till the new solutions become uniform. On separating concentrated solutions from water by semi-permeable membrane, allow passage of solvent and prevent solute. Water which diffuse from solutions of low solute concentration to solution of higher solute concentration. The diffusion of solvent through semi-permeable membrane is called osmosis. The solvent moves into the tube and the height of the solutions will rise till the hydrostatic pressure exerted by the column of solutions equal to osmotic pressure. You can see P is equal to rho GH. What is then the osmotic pressure? This is the external pressure that must be applied to the solution in order to prevent it being diluted by the entry of the solvent via osmosis. So osmotic pressure of non-electrolytes, non-ionized, osmotic pressure directly proportional to concentration. Twice concentration, twice osmotic pressure. Osmotic pressure direct proportional to number of molecules. Osmotic pressure of two molecules solutions having the same molar concentration are identical. For example, explain why. Solution contains 34.2 gram sucrose, molecular weight 342 in 1000 gram water, has the same osmotic pressure as dextrose. Solution, molecular weight 180, contains 80 gram per 1000 gram water. Number of moles of sucrose 0.1 molar. Number of moles of dextrose 0.1 molar. So that the two solutions are iso-osmotic. What is Van 't Hoff equations? You know friends, Van 't Hoff stated that there is a proportionality between osmotic pressure and concentrations and absolute temperature not applied in concentrated solution. Pi directly proportional to C, pi directly proportional to T, pi is equal to RCT. He suggested a relationship analog to the equation for an ideal gas, PV is equal to nRT. Osmotic pressure pi is a diluted solutions was equal to the pressure exerted by the solute if it was gas occupying the. So pi v is equal to nRT, pi is equal to nv by RT, pi is equal to CRT, pi is equal to mRT. Here pi osmotic pressure, T absolute temperature, N number of moles, B volume in liter, C molarity, mole per volume, and M molality. Here molarity and molality, here volume means liter, weight means kg. Pi is equal to CRT, Van 't Hoff equations. Pi is equal to mRT, Morse equations. Now friends, what is the osmotic pressure of 1 gram sucrose? Molecular weight 342, dissolved in 100 ml water at 25 degrees Celsius. So mole of sucrose you can calculate, and molality. So pi CRT is equal to 0.029 into 0.082 into 25 plus 273. Now osmotic pressure of electrolyte. They dissolve into ions, increase number of particles, so increase osmotic pressure. Sodium chloride ionized into two ions, each has the same effect on the osmotic pressure as molecules, so pi will be twice the solutions contains the same molar concentration of non-ionized substance. Potassium sulfate 3 times, ferric chloride 4 times. Now pi v is equal to I in RT and pi is equal to Im RT. I dissociation factor. For a strong electrolyte, I is equal to number of ions produced by ionizations of strong electrolytes in diluted solutions. For weak electrolytes, I is equal to total number of particles, ions or molecules divided by initial number before ionizations. For non-electrolytes, I is equal to 1. Now, vapor pressure logging. When non-volatile solute is dissolved in solvent, the vapor pressure of solvent is lower. Solvent molecules on the surface, which can escape into vapor, is replaced by solute molecules, have little vapor pressure. Why is vapor pressure lowering a colligative properties? For ideal solution of non-electrolytes, vapor pressure of solutions follow Raoult's law. The vapor pressure of solution P equals the mole fraction of the solvent X multiplied by the vapor pressure of the pure solvent P naught. So PA is equal to XA, PA naught. So PA vapor pressure of solutions, P naught A Vp of pure solvent, XA mole fraction of solvent, XB mole fraction of solute. So PA naught minus PA divided by PA naught is equal to 1 minus XA is equal to XB. So relative vapor pressure lowering PA naught A minus PA divided by PA naught is equal to the mole fraction of the solute. Now the absolute lowering of vapor pressure PA naught minus PA or del P of the solution is given by PA naught minus PA is equal to XB PA naught A. You can see here del P directly proportional to mole fractions of P. So lowering of vapor pressure is proportional to the mole fraction of solute. Calculate the lowering of vapor pressure and vapor pressure of solutions containing 50 gram dextrose, molecular weight 180, in 1000 gram water, molecular weight 80. The vapor pressure of water, it is given. So apply the formula vapor pressure lowering PA naught minus PA. You have mole fractions, you have the PA naught, then vapor pressure of solutions you have to calculate. Now friends, boiling point elevations. The boiling point of liquid is defined as the temperature at which the vapor pressure of that liquid equals the atmospheric pressure. So for a solutions, the vapor pressure of solvent is lower at any given temperature. Therefore, a higher temperature is required to boil the solution than the pure solvent. If we represent the difference in boiling point between the pure solvent and the solutions as del Tb, we can calculate the change in boiling point from the following formula. Del Tb is equal to I kVn. M molality, because molality is temperature independent. Kb boiling point elevation constant that depends on the particular solvent being used. Kb water is equal to 0.51. I want Hoff factor and represent the number of dissociated molecules, moles of particles per mole of solute. Now friend, freezing point depressions. Normal freezing or melting point is the temperature at which solid and liquid are in equilibrium under 1 atm. Addition of solute will decrease the vapor pressure and so will decrease the freezing point. In order for a liquid to freeze, it must achieve a very ordered state that results in the formations of crystal. If there are impurities in liquid, that is solutes, the liquid is inherently less ordered. Therefore, a solution is more difficult to freeze than the pure solvent. So a lowering or lower temperature is required to freeze the liquid. In analogy to the boiling point elevations, we can calculate the amount of the freezing point depression using the following formula. Del Tf is equal to minus IKFm. The negative sign because the freezing point of the elevation is less than that of the pure solvent. So here M molality, Kf molar depression constant that depends on the particular solvent being used, and want Hoff factor and represent the number of dissociated moles of the particles per mole of solute. Freezing point depression and boiling point elevations are direct results of the lowering of vapor pressure. So friend, colligative properties changes in vapor pressure Raoult's law. The vapor pressure over the solution is lower than the vapor pressure of pure solvent. Vapor pressure of solvent is proportional to the relative number of solvent molecules in the solutions. The solvent vapor pressure is proportional to the solvent mole fraction. So friends, colligative properties definitions. You can see the picture. So friends, hope this video will be helpful to you. If you like this video, then subscribe my channel, and thanks for watching.